graphs or maybe like
No, actually, I'm going to be a civil engineer. I'm going to never need this again, but I still need to not bad words.
That's why I picked this one. That's why I picked this. Because I was like, if this is going to be above the x-axis, well, first of all, if it's above the x-axis, this is above the x-y always.
Whoa, it was
Wherever it,
that was actually super
whatever region bounds where it is.
This have I showed you this before? This is cool. Wait.
Oh my god! Okay. This is Calc. This is a class. Oh, bro, that's wild. I love this class. This is the entire lesson. Everyone, 14.3 intro is best.
All right, that was on the I think I was recording. Yeah, I was recording. Okay. All right, so a reminder. In polar coordinates, x equals r cosine theta. Y equals r sine theta. X squared plus y squared equals r squared. And tangent theta is y over x. So all of our different conversions in polar coordinates. So what we're going to do today to develop the idea of double integrals in polar coordinates is if we have a region in the xy plane, we're going to divide it into what we call polar rectangles. So we have some region in the xy plane. So what we're going to do is subdivide this in terms of angles, like so. And we could keep going so we get the entire region. And then we would have, we would divide it into lines with constant radius. Like so. And I'm going to call this region, so we're going to divide these into, we call these polar rectangles. And I'm going to call this region here r sub I. So I'm going to divide it into a bunch of rectangles that are portions of circular sectors. So I'm going to zoom in on this r sub I, and we're going to come up with an expression for the area of that little sector. So if we look at just one sector in the xy plane, we get this. There's one of those pieces. So this is region r sub I. And I'm going to say that this is the radius equals A and the radius equals B here. And the angle here is delta theta. And this here would be delta r. And we call this a polar rectangle. This little r sub I is a polar rectangle. And we know that the area of the entire sector and the sector is the wedge shape there, the pie, the slice of the pie, is 1/2 r squared theta. So the area of the region that we're talking about is going to be, we're taking basically the big sector minus the little sector. So it's going to be our area is 1/2 b squared delta theta minus 1/2 a squared delta theta. So just to get the area of that one little piece.
Could you factor into 1/2 delta theta times b squared minus a squared?
That's exactly what we're going to do. We're going to say 1/2 b squared minus a squared times delta theta. And now I'm going to factor b squared minus a squared to 1/2 a plus b times b minus a. A plus b, b minus a, delta theta. Well, what's another way that we can think of this 1/2 a plus b? What do you get when you add two things together and divide by 2?
Average.
That's the average. This is the average radius. So in that region, that's the average radius, this quantity. So we're going to write that as our area equals r bar, meaning the average radius, and b minus a is delta r, delta theta. So that's going to be the area of that region. The average radius times delta r times delta theta. If we're finding the volume, that's how we defined our double integral, was by finding the volume. So the volume bounded by r under f of xy the volume of one prism so we're building, now we have a surface up above that region, and we're using that polar rectangle as the base of our prism, and the top of the prism is up at the surface. The volume of one prism is, I'm going to say V sub I is f of x sub I y sub I, where the x sub I, y sub I is the point in the middle of that polar rectangle, times delta a sub I. And in this case, our delta a sub I is going to be given by this expression, x sub I, y sub I, times the average radius of that particular piece, times delta r sub I, delta theta sub I. And we are going to express this in polar coordinates. So we'd say V sub I is f of r sub I cosine theta sub I. So we have to rewrite our function in terms of polar coordinates. R sub I sine theta sub I. And we get this quantity r bar sub I, delta r sub I, delta theta sub I. And the entire volume is the sum of these. I'm just going to write the sum, I equals 1 to k of V sub I, of this quantity. And then we're going to take the limit as the size of the polar rectangle approaches 0. And this is going to correspond to our definition of a double integral. So I'm going to switch pages here. And we get that the double integral over our region of f of xy dA, the volume of that solid bounded above by f of xy, bounded in the xy plane by that region, is approximately the sum I equals 1 to k, I'm just going to say of v sub I, where v sub I is given by that long expression. So what we're going to say in this case is that the double integral over our region of f of xy dA is going to be the double integral over our region in polar coordinates. So I'm going to write S to indicate that we've changed our coordinate system. The volume over S, double integral over S of f of r cosine theta, r sine theta. So we're writing our function f of xy in terms of polar coordinates, and then we get this quantity r dr d theta in the limit. This quantity r dr d theta is dA in polar coordinates. So in polar coordinates you will always have that quantity r dr d theta. That extra r appears in there because we had to take into account that average radius. There's an episode of The Simpsons where Lisa goes to a gifted school, and they're doing calculus, and the teacher writes a thing on the joke or on the board, and all the students start laughing, but Lisa doesn't understand, and it's because the integrand said r dr r r. RDR, RR.
I thought it was Bart that went to the gifted school.
No, it was Lisa.
No, didn't he score bad, or didn't he get his test mixed up with someone? And then he got sent to the gifted school and he had no idea what was going on.
Plastic hygiene.
I think that was a different. That's a different episode than the one I was
Back
thinking
one
of.
page, 'cause I see V sub I term.
V sub I is just this
That's
thing.
Okay, thank you.
All right, so for a double integral in polar coordinates, this quantity will always appear as part of your integrand, r dr d theta. And this S indicates that our region is defined by r and theta, not x and y. And to evaluate these, we're going to use a theorem. It's not exactly Fubini's theorem, because Fubini's theorem was for rectangular coordinates, but it's similar. To evaluate these, we evaluate them as iterated integrals. So to evaluate, the first case, we're going to say the double integral over our region of f of xy dA.
How many numbers are there?
2. Is going to equal the integral from alpha to beta, the integral from g1 of theta to g2 of theta of f r cosine theta, r sine theta, r dr d theta.
Is that supposed to be an S in the first one?
No. So we're transforming this double integral in rectangular coordinates to an iterated integral in polar coordinates. And we call this a radially simple region. So that's going to be a region that looks like a radially simple region looks like this. So this is theta equals alpha, theta equals beta. This is G1 of theta, and this is G2 of theta. This is our normal, this is going to be the most common way that we set up our integral in polar coordinates. And here we're setting up our little rectangles this way. And the second one is much, much less common, but we can evaluate them this way. We could say our double integral over our region, f of x, y, dA, is going to equal the integral from a to b, the integral of h1 of r to h2 of r. We still have to write our function in terms of polar coordinates. R d theta dr. And this is angularly simple. This is much, much less common. So our region would look something like this. We'd have nice radii that bound it, and our function along the side would look like so. So this would be r equals b, r equals a. This would be theta equals h1 of r, and this would be theta equals h2 of r. It's much, much more common to have r as a function of theta than theta as a function of r. And here we're setting our rectangles this way.
Are they rectangles or little arcs?
Well, they're polar rectangles. But this first order is much, much more common. I wouldn't, almost exclusively, but not. I wouldn't go as far as to say exclusively. All right, so what I want to do next is just go through some examples of setting up these integrals. Show some examples of when you might want to change to polar coordinates. It's usually pretty clear when you'd want to change to polar coordinates. Same time you'd want to change to polar coordinates in the xy plane. All right, so questions so far. Now, initially, the problems will say evaluate the double integral or find the volumes by converting to polar coordinates. Eventually, it will just say evaluate the double integral, and then you will need to decide, is it going to make more sense to convert or to use rectangular? So we want to find the volume of the solid bounded by z equals x squared plus y squared plus 3. Z equals 0, and x squared plus y squared equals 1. All right, what is this thing?
That's a That's this cone. Cone, yeah, it's a cone. No, moves up.
That's paraboloid.
Paraboloid.
Circular paraboloid.
It's a double nap.
What does the 3 do to it?
Tap out.
Shifted up.
Shifted up. So this is a paraboloid shifted up 3 units. So if we were to sketch a graph, we have this paraboloid up here. Z equals 0. What is that? Which plane? The xy plane. So we're bounded below by the xy plane. What is this? X squared plus y squared equals 1.
The region is a circle.
Circular circle.
That's a cylinder, right? So this is our region in the xy plane. What we're talking about is the volume inside this cylinder, but with this little scoop taken out here. So we have a tub of ice cream, and we have a parabolic shaped scoop, and we take a scoop out. We want the volume that's left inside there. All right, so in the xy plane, this is a quarter of the region. That's a fourth of the region in the xy plane. The region in the xy plane is a circle. When you see a circle in the xy plane, that's going to be a good indication that you're going to use polar coordinates. And since we have nice symmetry around the origin, we can say our volume is 4 times the integral, and we're just going to do the integral in the first quadrant. So in the first quadrant, theta goes from 0 to pi over 2. In this region, the radius, and I'm going to write this here, theta equals, the radius goes from what to what? 0 to 1. Our function, f of xy, z equals r squared plus 3. So that's our function. That's f of xy, r squared plus 3. And our dA is r dr d theta. What does the d theta integral do here? It multiplies it by theta evaluated from 0 to pi over 2. That's just a multiple of pi over 2, right?
Right.
So we get 4 pi over 2. This we can evaluate. We can switch the order of the theta in the r integral because none of this depends on theta, and then we just get the integral from 0 to 1 of r to the third plus 3r dr.
I'm just never gonna do that.
I'm just gonna do it how
I'm just gonna solve the top integral. Like I can do this too.
Oh my god.
So what I'm saying is this bit r squared plus 3 rdr doesn't depend on theta. So I can just evaluate the theta integral. It's just theta from 0 to pi over 2.
So you can separate them if there's nothing on that inner part that
Right.
has anything to do with theta. So if it's
Right.
all r's, because the only
Yeah.
r part,
Yeah.
just get rid of the theta part.
Well, you don't get rid of it. This just is a constant multiplying the integral.
No, you don't.
It's fine if you want to evaluate the inner one first, and then multiply it by the d
You
theta,
said that you already know it.
the integral of d theta. It just adds a multiple of pi over 2. And this is a nice, easy integral to evaluate. We get 7 pi over 2. So the volume of that thing is 7 pi over 2.
No days off.
All right, questions? All right, let's look at another one. We want the volume inside the hemisphere. Z equals the square root of 16 minus x squared minus y squared. And outside, the cylinder, x squared plus y squared equals 1. So what we have here, I would suggest drawing a little picture. I'm just going to draw it in the first octant. Here's the hemisphere. And here is the cylinder. So we want inside the hemisphere and outside the cylinder. So we're talking about the bit that's out here. So really, what we're doing is drilling a hole into a hole into the hemisphere. All right. In the XY plane, here's our region. In the first quadrant. Or that's a quarter of the region. Here the radius equals 1. And here the radius equals 4. So another way that we could ask this question is the volume under z equals the square root of 16 minus x squared minus y squared bounded by r. That's another way you could be asked the same question. All right, so this is a nice symmetrical region. So we can say our volume is 4 times. Theta goes from 0 to pi over 2. R goes from 1 to 4. The function that we're evaluating, 16 minus x squared minus y squared, square root, 16 minus r squared. And then we have r dr d theta. This situation shows up a lot in polar coordinates, especially when you're talking about nice quadratic surfaces. We have a square root of 16 minus r squared, but then our dA is r dr d theta. So this is a nice use of it.
And we can get rid of this is another one where we can use beta.
Right. The r portion doesn't depend on theta. So you can evaluate that integral. That just adds a multiple of pi over 2.
Right. Do the same thing.
So I'll do it without doing that bit. We're going to do 4 integral 0 to pi over 2. The integral of 16 minus r squared, r dr d theta, is what?
So 1/3.
1/3. Is it positive or negative 1/3?
Negative.
Negative 1/3. There we go. 16 minus r squared to the 3 halves. And we're evaluating that on 1 to 4 d theta. And when we evaluate this on 1 to 4, we get 4 integral from 0 to pi over 2 of 1/3. What's that?
Pi is should be pi over 2.
Oh, thank you. 1/3 of 15 to the 3 halves. D theta. And then, so what I was saying before, so we get 4/3. The integral of theta, we get 15 to the 3 halves. Theta evaluated on 0 to pi over 2. That's just a multiple of pi over 2. None of this depends on theta, so we just have a multiple of pi over 2 at the end. And we could write this as 10 pi square root of 15.
So does that happen frequently where you could just do the thing with the theta?
Yes,
like right
it does.
up front?
It does. Not always, but frequently. All right, now we've had some nice symmetry. I have a question for you.
The answer's pi.
How long is this one?
Is that a circle or an
That it's a circle.
There you go. Pecan pie. Pecan pie.
This is a circle with the same radius. And now I'm going to say this. Let me undo that. That is R. And this is a true or false. Or how about, no, I'll do it this way. Always, always, sometimes, never.
It's almost always. Of course
The integral over our region of f of xy dA, I'll call this R1 and this R2, just so we can keep them straight, equals 2 double integral over R2 f of xy
That's not.
dA.
It's sometimes, right? You could make it so that's true if you just have like a plane or something, because
Right, what does it depend on?
it depends on what the function above is.
Right, it depends on f of xy. If f of xy is symmetrical about that region, then yes. But if f of xy is not symmetrical about the region, you cannot do that. So you have to be careful when you want to multiply with multiple integration. You have to be careful when multiplying by a constant.
So the way you would have to approach that, so let's say we had a region that was not symmetrical anywhere for R2, you would have to set up two different integrals, one that goes from 0 to pi over 2, and then another that goes from 3 pi over 2 to pi again, because you couldn't do any symmetry. You had to go around in order, right?
For this one,
For R2.
R2, you could go from negative pi over 2 to pi over
You
2.
could set up to be
Yeah.
one, but if you wanted to go all positive, you have
Yeah.
to use 2. Okay.
Right. All right, so my point here is be careful when you decide to multiply an integral by a constant, because it does depend on f of xy, whether or not you can do that. All right, let me see what else I want to do here. Let's find an area. So let's find the area of one petal of r equals 3 cosine 2 theta with a double integral.
They're back.
Yeah, I'll take that pi.
We should draw a picture.
All right, so let's draw a picture. It's a cosine function, and it has 2 theta. Do you remember how many petals it has?
That's 3 petals. 4 petals.
4 petals. So it's going to look, my rose curves are not beautiful and perfect, but it's going to look something like, it's going to look something like that. And I'm going to, I'll tell you, so this you would either need you'd need to be given some information, or you'd need to be able to graph it, something. I'm going to tell you that half a petal is traced from 0 to pi over 4.
And tools to graph it, or some other.
Right. So we get this half of the pedal between 0 and pi over 4. Now the thing with the rose curve is this pedal is graphed from 0 to pi over 4, but then from pi over 4 to pi over 2 it graphs a half of another one.
Oh, see, these are different.
Yeah,
So
it's
what
totally
we're gonna do
different.
is like how you know what the angle is.
So can you just go to 0 pi over?
I would say set this equal to 0. Set r cosine 2 theta equal to 0 and solve for theta.
But since it's all symmetrical, you could.
So we're going to integrate find the area. We're going to find the area of a quarter of a pedal
Or half.
and multiply, or half of a pedal and multiply by 8.
It only said find the area of one pedal. We need to multiply only by 2.
Yeah. We just do
Oh.
it from 0 to by half, and then you'll get one whole pedal, right? Mr. Beamer?
How about that? Area of all pedals. We want the entire area.
Mr. Beamer,
Uh-huh.
we do it from 0 to pi over 2, we get one pedal? Or we get, that's not how it traces.
Right. It doesn't trace. Right.
It traces it
It,
like
it
this.
traces like this.
Yeah, but you'd still get two pedals within that area.
One will be positive,
Yeah. All right, so let's set this up. Our area equals 8. Integral from 0 to pi over 4. The radius goes from 0 to... So our radius is going from the origin to the curve. 3 cosine 2 theta r dr d theta. The integral of dA gives us our area.
So once again, we can do the thing to get rid of the theta.
We can't because this depends on theta. Here we cannot do that. So let's evaluate our first integral. So we get 8 integral from 0 to pi over 4 of r squared over 2 evaluated on 0 to 3 cosine 2 theta d theta. So we get 8 integral from 0 to pi over 4 of 3 cosine 2 theta squared. And I'm going to write this as 1/2 d theta. Does that look familiar? Area in polar coordinates in the xy plane. 1/2 r squared d theta. 1/2 r squared d theta. And this is just like when we were finding the area of a plane region in the xy plane. We got top function minus bottom function. All right, now let's think about this. How do we evaluate the integral of 3 cosine squared 2 theta?
Power reduction. Table with integrals.
So this is going to equal 36, the integral from 0 to pi over 4 of 1 plus cosine 4 theta over 2 d theta. This integral, now that we're talking about polar coordinates, cosine squared of something, sine squared of something, shows up frequently in polar coordinates, in spherical coordinates, and in cylindrical coordinates. You'll see this quantity a lot. When we evaluate this, I'm not going to keep going. This equals 9 pi over 2. So the area of that rose curve is 9 pi over 2 square units. All right, questions? Yes. All right, before I give you your homework, I'm going to give you another task.
Is it a pie eating competition?
Yes.
I did.
I've got to find it now. So, listen up. This is what while you're eating pie, this is what I want you to work on. So we want to calculate. The integral.
So is this starting activity?
Yes.
Why are we doing it?
I don't want that.
Yeah, stop complaining.
Oh, this was on the homework.
You get pie, boy. That's why. By changing
Oh. It's almost like why.
So we want to change this to polar coordinates. Part B. Part 2.
Whoa. We're gonna eat pie, Mr. Beer.
Show that this is equal to 0 to infinity e to the minus x squared dx squared.
But that's impossible.
Using 1 and 2, calculate 0 to minus infinity of e to the minus x squared dx. So this is those of you that are in stats. You know that for the normal distribution, you have a normalization constant. That 1 over square root of pi.
Yep.
This is how you find the normalization constant.
Yeah, I have.
I'll be honest, I haven't learned anything in stats.
There's only one stats class that might actually know it.
That's not what you told me every day. You told me
All right. Oh, yeah, and I forgot this. So that's your activity. I can put this back up on the screen in just a second. Homework.